Alright, to solve work problems mathematically, there are two versions of one formula, and it's helpful to just remember both. First, work equals force times displacement. This equation only applies when the force and the displacement are in exactly the same direction, no angles involved. So if they're in exactly the same direction, you just multiply the force times the displacement. Super simple, and that's the work. As your book told you, when you get done, the unit for work is joules or J. So the J stands for joules, which are the unit for work. Now, this next equation, you're tempted probably to just look at and say, oh, that looks easy, I can remember that, or oh, that looks easy to use. Memorizing the equation will not be good enough. Just like with kinematics, just like with forces. You have to actually know what's going on, so pay special attention to the next couple minutes of the video as I explain what's actually going on with this equation. There's more to do than just remember the equation or how to use it. You have to understand the physics behind it. So remember the definition. When a force moves a distance, work is done. Well, what if a force moves something a distance, but part of that force doesn't move the thing? What I mean by that, we have a force in this second diagram that is at an angle. So only the x component, and I'll draw the x component in blue, only the x component of that force actually moves this box a distance. That force also has a y component, and the y component of that force does not cause the box to move. The box is not moving upward, it's moving to the right. So only the x component of the force causes that box to move. So when we find the amount of work done, we will only deal with the part of that force that actually did the moving, the x component. And if you look here in this diagram, the angle touches the x component, making it an adjacent side. And so here we would do work equals force cosine theta to find the x component of that force times the displacement, times how far it moved. Only the part of the force in the same direction as the displacement does work. Such an important fact, I'm just going to type it out and have it on the next slide for you to write down. But in this problem, you have to find the part of the force that points the same way as the displacement. It may not always be as simple as just looking at it and saying, oh, it must be the cosine part. I might give you some crazy problems where you actually have to figure out what part of the force, what amount of it, points in the direction of the displacement. Just like with forces in kinematics, I wasn't always nice. The AP test is not always nice. The x part doesn't always have to be cosine. What if that box moved up? In that case, it would have been the sine part over here. So, just remember you're looking for the part of the force in the same direction as the displacement. Alright, here's the slide with the fact you need to remember. Only the part of the force in the same direction as displacement does work. Take a second to write that down. Pause the video if you need to. I'm about to go on to the next slide. Going in 3, 2, 1. Alright, 3 problems to try. Why don't you go back and use your notes from the last slide. Try these 3 problems. Come back for the answers. So go ahead and pause the video. Try the 3 problems. Okay, you've hopefully now paused the video. I'm going to minimize this slide so that we can talk about what's going on. A 1300 Newton crate rests on the floor. How much work is required to move it at a constant speed? First, 4 meters along the floor against a frictional force of 230 newtons. Okay, well this problem is interesting because it doesn't actually tell us how much force is applied to the box. It tells us there's a frictional force of 230 newtons. So this ends up being an equilibrium problem, first of all. If it's moving at a constant speed, that box is definitely in equilibrium, meaning that the pushing force would have to be equal to the frictional force. So if the frictional force is 230 newtons, so is the pushing force. Also, if the box moves horizontally on the floor, that means that it moves to the right, so my force and my displacement are in the same direction, meaning that my work's going to be positive, so whatever number I get will be a positive number. And now I can go ahead and plug in my numbers. Since they are in exactly the same direction, I'm just doing force times displacement. Work equals 230 newtons times 4 meters for the displacement, and I get work is 920 joules. Now if you're wondering, why did I call this displacement if I didn't write a direction? Well, I did. Look, right here, over here. I said it was to the right. I also said my force was to the right. So I used both of them as vectors, and looking at what direction they went helped me figure out whether my work is positive or negative. So this is positive 920 joules because the force and the displacement are in the same direction. As Jay-Z says, on to the next one. In the second problem, we have the box again moves 4 meters along the floor using a 500 Newton push at a 10-degree angle below the horizontal. So that would mean angle of 10 degrees right there. And I'm going to do these on the same slide, just color code them so you'll know which one I'm working. The box still moves along the floor. Here, the force and the displacement are not in exactly the same direction, so I have to use work equals force cosine theta, and the part of the force directed in the same direction as the displacement is this part here, which touches the angle, so it's adjacent, so we are definitely using cosine. Want to check that, make sure it's not a tricky one, and then times the displacement. So now I plug in my numbers. Work equals 500 newtons times the cosine of 10 degrees times the 4 meter displacement. I got that 500 times the cosine of 10 is 492 newtons times 4 meters. 492 times 4 would be 1,968 joules. And I'll go ahead and do this next one on a different slide so things don't get messy. Alright, now it says what if the box moves 4 meters vertically? And since it doesn't give me a force, but there's a force vector there, or at least that arrow's been the force in the other problems, let's go ahead and assume it's the same as last time, 500 newtons. Notice that my force and my displacement, if the box moves up vertically, are in the same direction, so my work will be positive, a positive number whenever I find it. And since they're in exactly the same direction, I just do force times the displacement. So work equals 500 newtons times 4 meters. Work is 2,000 joules. It's a J, by the way, joules. Now, something to pay attention to. If at any point my force and my displacement had been at right angles, no matter what their numbers are, displacement, the work would have been 0, no matter what their numbers were. And if at any point my force and my displacement had been in opposite directions, my work would have been negative. And if they'd been in exactly opposite directions, I still would have done work equals force times displacement, but at the end I would have made it negative because they were in opposite directions. For anything in between, so if we've got something that's not quite a right angle for my displacement, cosine takes care of the sine for you, and you'll see some of this tomorrow. The cosine function actually determines the positive or negative for you in situations where it's unclear. But if it's at a right angle, it's definitely 0, and if they're in opposite directions, it's definitely negative. And that's it. Be sure you know all this stuff coming in tomorrow, and we'll jump right into discussion, questions, and problems. Have a good night.